The fundamental engineering challenge of the modern world comes down to a single task: taking isolated, distinct entities and linking them into a unified web. Whether you are dealing with remote villages, independent computers, or regional power stations, they are completely inert without a physical connection allowing them to communicate and share resources. But building these connections requires finite, expensive resources. Every mile of highway demands tons of asphalt and intense manual labor. Every network link consumes miles of copper cable or steel. This creates a massive paradox for engineers. If you tried to connect every single entity directly to every other entity, you generate a chaotic tangle of redundant infrastructure, and your financial costs spiral out of control. Network engineering focuses on reaching a precise point of equilibrium, maintaining total system connectivity while minimizing the physical resources required to sustain it. To solve this infrastructure waste, we must look past physical materials and turn to mathematics. We need to isolate the exact bare minimum structural backbone required to keep a system alive. In computer science, this structurally perfect backbone has a formal name: the minimum spanning tree. A minimum spanning tree guarantees that every node can communicate with every other node, but it does so without a single redundant link. Understanding how an algorithm computes this global optimization requires deconstructing the network to its basic rules. So we will wipe the slate clean and build the mathematics of networks from absolute zero. We start with a graph, a mathematical structure designed to map relationships. These individual objects are called vertices or nodes, which could represent cities or routers. The lines connecting distinct vertices are edges. Together, they form a core formula. A graph equals its vertices plus edges. Notice these red numbers appearing. Edges carry quantitative costs, like kilometers, milliseconds, or dollars. When we assign costs, we call it a weighted graph. For our optimization problem to even exist, this graph must be connected. That means there is an uninterrupted path allowing any vertex to reach every other vertex in the system. When you have a fully connected graph with many edges, you will inevitably encounter circular paths. Here, you can travel from node A to B to C and right back to A. This closed loop is called a cycle. It occurs whenever you start at a vertex and return to that same vertex without repeating an edge. In network optimization, the cycle is the direct source of financial waste. If you can reach node C through node B, a direct line back to A is a redundant edge. Watch what happens when we break that cycle. We change the structure's classification. We now have a tree, a connected graph with 0 cycles. This chart highlights a strict law. A tree with n vertices always contains exactly n-1 edges. 4 vertices require 3 edges. 5 vertices require 4 edges. Any structure that qualifies as a tree has achieved maximum structural efficiency. It uses the absolute minimum number of edges to maintain connectivity. Let's apply this to the massively interconnected networks we find in the real world. Raw infrastructure graphs are densely packed with redundant loops. The engineering challenge is taking this dense graph and extracting only enough edges to keep every original node connected, stripping away all the excess. When we extract this efficient subgraph, we call it a spanning tree because it successfully spans across all the vertices of the parent graph. It must use every original vertex, it must contain 0 cycles, and total n-1 edges. But within a single, highly connected network, there isn't just one answer. Notice how there are multiple valid configurations that satisfy the rules of a spanning tree, carving different paths through the same nodes. While any valid spanning tree ensures basic connectivity, it does not guarantee financial efficiency. Because edge weights vary, some spanning trees will cost significantly more to build than others. This brings us to the core problem. Out of all possible spanning trees in a network, which configuration yields the lowest total edge weight? Comparing two trees. On the left, edges weighted 2, 3, and 1 cost 6. On the right, an alternate path costs 9. The left configuration is our minimum spanning tree, the unique tree with the absolute minimum total edge weight. Identifying the cheapest path in a 4-node graph is simple, but how do algorithms compute this on global networks, where checking every combination is impossible? They rely on a logic paradigm called the greedy method. It doesn't attempt to map the entire future. It simply makes the cheapest, most selfish local choice at every single step. By strictly selecting the lowest cost edge available and rejecting any edge that creates a cycle, the greedy method constructs the global minimum spanning tree. These abstract definitions translate directly into the physical systems that move power, water, and data. When engineers build a regional electrical grid, they use the properties of the MST to connect houses using the bare minimum length of high-tension wire. When municipal planners design water systems, they rely on this logic to calculate the cheapest subterranean routes, minimizing the cost of laying heavy steel pipeline. In microelectronics, designers map out printed circuit boards as graphs, using the MST to reduce wire length and prevent signal delay. And in digital communication, it provides the baseline logic for routing data through local area networks without creating endless feedback loops. Whether the edge weight is measured in tons of steel, voltage drop, or network latency, the mathematical model remains universally applicable across these diverse systems. To cement this sequence in your mind, remember how we prune complexity into perfection. We start with the raw graph, representing the total network. We apply our first filter, removing the cycles to create a standard tree. We enforce our connectivity rule, ensuring all original vertices are reached with exactly n-1 edges, giving us a spanning tree. And finally, we apply our greedy logic to select the lowest possible physical or financial weight, leaving us with the minimum spanning tree. Now that you understand what the minimum spanning tree is, we are ready to solve it. In the next session, we will execute the precise, step-by-step logic of Prim's algorithm to uncover the perfect network.